implementation. So you don't have to. Let's this example again. So if you have something like this, so if you have a list, I just generate a list out of a string, make a list that looks like this, and I have a second list with other letters, yeah. And I would like to find out which one are on both. Then yeah, I can do a very naive implementation using lists, and I get a quadratic algorithm. So we come to this order in a minute. So I just have a new list, and I go to my first list, and for every element in my first list I go to the whole second list, and if they are on both, I append it if this one is in here. So this if one has to check the whole list if it's in there, then append it. So, and of course this is not very efficient, because I have to, for every element of the first list, I have to potentially go to the whole second list. So that's not very interesting, because only if it's in there it's appended. I actually have to go through, and then I get this result. So if you do sets, it's nice, because then you just create two sets, and even the algorithm gets simpler, because it just boils down to say intersection is doing the same thing. So that's a nice optimization, because it makes things shorter and also more talking, because if you know what the intersection means, you immediately see that's intersection, unless with this double loop there with a list which is not that easy to understand. So now I have just a test function which is generating two lists here, and just doing this with this time it, and just measures how long it takes in this case. And you see, if I do intersect this list, this function, if you do it, takes about 1 to the power of -5 seconds. Now we do the same thing with sets, the same function, just instead of a list I use a set. So just wrote it very verbose, so it's easy to see. And then I do the same thing, and here the run times, even for 10, it's faster already. So if I make a bigger, so if I compare them both again to see the ratio, same thing, just a helper function, and then I do this running, and you see if it's 10, it's about 2 times faster, 100, 50 times faster, 1,000, 500 times, and 10,000, 7,000 times faster. So it's a very, very big difference. So it's 5 orders of magnitude difference if you just use sets, and in addition it's easier to read and it's shorter. So whenever you think you could use a set, of course you can implement it with dictionaries. You just go to the first dictionary keys, and the next one you just do an in operator, or then you would get some similar performance, because intersection is doing something like this in the background. But sets is even nicer, because sets are made for this type of work. So intersection is one, but you can also get the difference between two sets in both directions, and a few other things, everything that you might know about sets in a mathematical sense. Okay. Another one, now I would like to go to a few kind of additional data structures that Python offers. They can be useful for a few of things. And one is called the DAG. It's a double-ended list instead of a normal list. Because we have a list. It's very nice for appending. You can append things at the end. That's what the list is made for. You don't want to do an insertion in the list in the beginning, because every time you search something in the list, then you have to recreate the whole list, because you change the whole structure of a list, which is pretty inefficient if you do it often. But for some use cases, a DAG can be interesting. It's a different data structure. So for here now, I just write a small function profile speed, which is actually using EuroPython converter to convert something, and again uses a decorator to wrap a function. So again, this is an outer function of the decorator, takes a function, and this one is this wrap thing to make the decorator look nice, takes the arguments, and I just do this, what I just did manually here now with the decorator, it's the same thing. And I calculate the runtime, and also calculate the kilostones here, kilopystones we did in the morning. And then I just store speed. Speed is a global dictionary. I store just again the same function name, and then store the time in the keystones. So if I do this, I can run my program, and then you can import this thing and can profile. So the only thing you need a decorator function you would like to profile, and I would like to remove something from a list. And a very easy way to do this in Python, you just specify a start and an end index, and then you assign an empty list. So you don't have to go through and delete everything. So every time you delete would be, usually you want to, if you minimize the number of lines you write in Python, usually it's faster. So it's only one operation here, and the rest you give to Python. And most of the time this is faster than writing a loop yourself and deleting everything. So that's probably pretty efficient already in terms of what you can do with a list. And I just delete a few elements out of my list by assigning an empty list. Yeah, so you can always have this slice assignment, and it doesn't matter how big the slice is, just has to be a list also, and then it's just going to replace it. Now we do this with a DAG. So a DAG is a different data structure. So I actually have to say from collections import DAG, and we'll see this. So if you DAG is a data structure that lives in the collections module. The collections module is very interesting. It seems like with every Python version, it gains a few new interesting new features. And so from collection import DAG. So this is this data structure, collections is a plural. So collections. And now I have this DAG, and I can create a DAG, and looks like this. And this DAG now you can access from both sides. So you have a few things you can do with a DAG. You can append left. So that's something different. So the list doesn't have append left for good reasons. If you want to do this with a list, you have to say to insert 0, which is a very expensive operation because you have to recreate the whole list. And a DAG is different. And a DAG has something called a rotate. So if I look at the DAG again, looks like this. And I can say rotate. And I want to rotate 3. And I look at my DAG again. See, now everything is rotated. It's like, you see this 9 used to be the end. Now I rotated everything around by 3 positions, and the 9 made it to index 2, so at position 3 here. And of course I can rotate the thing, I can rotate things back. I say rotate -3, and back I am to my DAG. And because the thing is, you rotate things because working at both ends of the DAG is very efficient. So you don't want to take anything out in the middle, but if you do it at the end, it's very efficient. That's why you rotate the whole thing, work at the ends, and then rotate it back. And for some use cases, that's more efficient than just taking things out in the middle. So we have a look for which use case it is good. That's what I do here. So I get my DAG and start an end, and that's what I'm doing now. I rotate everything to the -n, so I rotate it to -n, and then I pop off. So pop is the same we know from lists. Pop means just takes the last one and pop it off. So, and I do this end minus dot times, pop off, and when I'm done, I rotate it back to the start. So I just turn it there, pop off the ones, and then rotate it back. So this means I take things out of the middle without going to the middle directly. I just I work at the end, and that's what I want with this DAG. So I work at the end. So that's what the thing is doing. And now, you see that's my list example. And if I do it with a DAG now, from this number 0 to then, and I rotate it. So that's just an example, which is just what I did, what I showed you. And then I pop things off, and things go back. Yeah. So that's what you can do. And now I make a big list with 1 million numbers, and I import my DAG, and then I make from the list I make this DAG here, and then I call these 2 functions, one with a list, the other one with a DAG, and then I compare, and I use just my decorator, and then I see how long it takes. So I do the first one, and I just give them here, and you see this. If your decorators run it, then it puts it in this profile speed. It's a module name, and speed is a global dictionary, and it puts a function name in here. And here see, remove from list takes 1,000th of a second, and remove from DAG takes 200,000th of a second. So that's a big difference. That's about 2 orders of magnitude difference already for this list with only with a million elements, and I want to remove just 5, 100 to 105. Yeah. Okay, that's the first thing we do, and you see the ratio is 70 times faster. I said, yeah, more than 2 orders of magnitude difference. So if I do this again, but now we don't remove only 5, we remove 900 elements from 100 to 1000. And you see a different result if you do this. Now if you do this again, and we do this comparison again, then we're only 5 times faster. Why is this? Because now we had to rotate, and we had to call pop 900 times instead of 5 times. And if you make it even larger, if you remove 10,000 out of a million, which is still not a big thing, then now we're slower. It takes twice as long with a DAG. So again, if you have a large data structure and just want to remove a very few in the middle, then a DAG might be a good solution. If you want to remove a lot of them, a DAG is not a good solution. So your data structure, the algorithm depends on the data and what you're going to do with the data. There's no clear solution. You say DAGs are faster than lists. No, that's not the case. You have to really try it out for your data you have, how they are structured, how big. So if it's a list with 100 or 1,000,000, it's very different. And also what you're going to do with it. How many elements do you remove? And then you see different effects. So that's very often, so I always encourage you to measure, even if you know this is faster than this, it is always a good thing to measure, and measure a few different scenarios and see what's going on, and you might see an undesired effect here. Okay, so that's one data structure that in collections. Another data structure I will show you is default dict. Default dict is a pretty interesting data structure because it also has a side effect making your code shorter. We see with this DAG we had to write more. The list was just 1 line. With the DAG we had to write 3 lines and rotate back and forth. So we had to put more effort in, and you have to make sure that's useful. The other one is a default dict, which can be nice because it can make your code shorter. Now we have this example. We just have some text here, and you want to count how many times each letter appears in the text. So you just do set default. So set default is in Python. I think most people know. Just quickly to remind you what set default is. If you have a dictionary that has a key A and value 1. Just move it up a little bit here, so down at because every time it logs out, it just comes out. Move this. So I have this dictionary, and I can use set default, and if I just access A, it will just give me back the 1, and I can specify an optional default value, which again defaults to none if you don't want to. So see, if the key is inside, nothing happens. The dictionary just the same thing as I would access the key. But I can also say, give me B, and B is not contained, so I get the default value. And since it's called set default, at the same time it's putting the default. So that's what I'm using here. So I don't have to try something and check for a key error. I just can use set default. And if it's not in there, it will just set. I don't care for the return value here. I just set 0. So if it's not there, I will initialize my dictionary with 0, and then I can add how many times this letter is in there, and I know how many times the letters are in there. So that's what I do, and you will get something like this, and tells you how many times. So you can use default dict, and default dict is a bit different. So default dict is you specify what happens in this default case, and in this case I just give it a constructor for int. So int is gives you a new integer. So if you call int in Python, you get a 0. So that's a 0. So we would initialize with 0. So you're doing essentially the same thing, but you only write 1 line. So instead of writing 2 lines, you only write 1 line, and then you can just set it. So you have from 2 lines of Python you're down to 1, and you will get pretty much the same result, only that you get a default dict instead of a dict, but you can use a default dict as would be a dict, just can access keys, do everything. Only thing, if there's nothing there, then this default thing would kick in and would give you a 0. So if you access it here and add something, it would call, like set default in the background for you and call int and put a 0 in there, and then you have the same effect. So and if you do this, then now we do this just here with our profiling function, and have the first implementation and the second implementation, and then we compare both, and you see if it's a small one you're a bit faster, so it's not a lot in this case, and we make a bigger one with 1,000,000 A's and we count, and then you're twice as fast. So it's not, you don't get an order of magnitude, but you get a bit faster and you can be shorter and you can write nicer algorithms. So for some things this default dict can be useful, and you might have a different use case and you can try out, you might gain more, I don't know. So this always, again, you have to measure, because sometimes you can be pretty wrong. So what happens, as we've seen before. And the same thing now, have just a different example. So you want to have this from Python documentation, you just want to sort this color things here. There's groups, so things by the entries. You see blue is here twice with 2 and 4, and you want to group it this way, and you want to get it out, then you can use the default dict. That's a very nice use case. So it's not for the performance. This case is just doing the default dict, and we do it again. We measure how long it takes, and we feed it some data inside. And see, in this case, it's not faster. So if you use this very small one, then the default dict for some reason is slower than our normal dict. So it doesn't really, it's always, usually if you have small data structures, then the performance is not that important anyway. And you might get different results when you have big data structures, as in this case. If you increase the number, then you get faster. So now I go up to 10,000 times this data and put it in, now we are about twice as fast. So makes sense for big. If you have a lot of very small ones, it doesn't really make sense for speed reasons to do it. It's easy to read, and if it's small and doesn't matter too much, you can still use it. So it's a bit slower, but not that much. And if it doesn't really matter, you can use also this default dict. So that's a few of those things in collections. They can be interesting. There's also a few other ones. There's like order dict in collections, which is very efficient. So if you need a dictionary that preserves insertion order, like if you want to serialize something, a dictionary, and you want to serialize in a way from a dictionary that the user can edit it and read it back, then you don't want to use a dictionary, because every time the order can be different and drives the user crazy. Then you can use the order dict, which preserves the order. This is also in collections. So there are some nice, interesting data structures. So I encourage you to have a look at collections. Okay, so we worked with data structures, and data structures and algorithms are closely related. And this is what's called the big O notation. So it tells you how those algorithms behave, how the runtime behaves with a growing data structure. And there's one is called O1, which is constant in time. So the runtime doesn't change no matter how big the data structure is. And this is always a preferred one. So if you call length from list, then it always takes the same amount of time, no matter if the list has 1 element or 10 million. That's constant in time. The same if you do the length for other ones. If you delete something, that's constant in time. If you use if you use the X in dictionary, so it's a lookup in a hash table, it's also pretty much constant in time. You can try it out. No matter how big the dictionary is, it's pretty much the same length it takes to look it up. Also, append is constant in time, which is interesting, which is due to this memory effect I showed you, which is very nice. The other one is linear, so if you double the size of the data structure, it takes about twice as long, pretty much. And this is if you loop over something, or if you look for X in my list, it takes about constant time. So this is still okay. So of course it would be much more preferable to stay here. So if you have a dictionary to look in, that's the list, but it's still kind of okay to look in there. Then sorting in Python is very efficient. So because sorting in Python is doing a lot of tricks in the background, it tries to take advantage of or it's sort of order and things like this, and it's called quasi-linear, so it's n log n, so it's not really, it grows a little bit faster than the linear one, but it's still acceptable for a lot of things, and sorting, I think it's a good order for sorting already. And then now you get into the area where you don't want to be. Quadratic means if you double your data structure, takes 4 times as long, and if it's 10 times as big, it's 100 times as long. So that's kind of explodes very quickly. And this would be a nested loop. We have a loop as we had before, and then another loop. So that's a pretty thing you want to avoid. And everything else, then if you do a loop of a nested loop, then you get very, very, very bad runtime performance. And everything else that's higher than factorial, that's even higher than, you very, very quickly, with just a few very small data structures, very quickly, you just have very, very long runtimes which are impossible to solve, and you have to wait for the quantum computer to do this. Okay, just a few examples, though. This what you can do now. We have this O1, so it's constant in time against this linear and the quadratic one. I just have again we use our profile speed function here, and we have a function that we profile that takes iterable and has a result. And now we do something you shouldn't do in Python. It's anti-pattern. So we go through our iterable and we say result insert 0. So we insert something at the position 0 every time. So in our list in this case, and that's something that's not really nice. It would be better to always append things and at the end reverse your list. So if you compare both, this one is ON, this is O1 here, and now I've just used both and I just make sure both give the same result, and you compare them, and then you see, depending on the data size, how much more time it takes. So if it's small, there's no big difference. 1.6 is some difference already, and you go up here 1,000 is 4 times, 10,000 is 27 times, and so on. You see how much penalty you pay for doing this insert 0 instead of converting it. If you have 1 million elements, it takes 2,300 times, and if you run this, it takes quite a few seconds, because every time you do the insert, you have to recreate your list, allocate everything, and do everything, and it's getting very expensive. Of course, it depends also on the operating system, how it handles memory management and stuff like this. But this is also an anti-pattern, so you should never, if you do this a lot with this insert 0, then it's a good indication that you're doing something wrong, and you should go for something like this if it's possible. Sometimes you might not be able to avoid it because the algorithm is like this, and you do other things, and I don't know. But if it's possible, you should go for this. Of course, if you do this, and every time you call reverse, then you don't gain anything, because you have to reverse the whole list. So then you have to go through the whole list, and you will pretty much probably be slower than the other one. You have to try it out. I don't know. Okay, that's one. And now I just have it. Okay, now I do this. What do I do here? Yeah. This is it. This append. Okay. Yeah, this is just a measurement how much longer it takes. Okay, so we can reverse the result. Yeah. The same thing again. Okay. It's an exercise. Go to the next one. The next topic is caching. So we are through with our algorithmic things, and the next topic is caching, which can be very interesting for a few things. And we look at a few examples how to do caching, because we can distinguish between two kind of caching. So every time you calculate something, and you do over and over again calculate pretty much the same thing, then you can do some kind of caching. So let's look at some examples. So I have two examples. First, we have a function called getKey. Usually, when you cache something, you put something in dictionary. And to do this, you have to... So I'll make it bigger for the people in the back. So if you do this, you need to have some function to generate a key, depending on the signature of a function caller. There's different ways to do it. Some people use like pickle to do something like this. And this is one way here from Tarek CAD. He recommends, so you generate a key, and what you take the function module name and the function name. So that should be pretty unique, because every module name can only be once. And of course, that's how Python works. And every module should only have only one function with the same name. I think you can define two, but then the last one would win. So, but there can only be one function, so you use a function, the name, and generate a string out of those two, and then you generate another string, another part of the string from the arguments. So you get arguments. So the star args are all the positional arguments, and double star keyword args are all the keyword arguments. And you just go through and convert them to strings, and you do the same thing for the key and the value. So we can convert all of them to strings. And then we generate a key that looks like this. So we just put our function name in here, which is a key here, module.name, and then we put all the positional arguments and all the keyword arguments, and there is string. So this would make a string which is unique for this one function call, and every function call is the same function, the same module with the same arguments should produce the same key. So it should work for everything that can be converted to a string in one way or the other. So if it doesn't have a string somehow, so if you write your own object and you override str and don't allow it, then it might not work. Okay, let's look inside our deterministic caching. So cache deterministic it's called, and it looks like this. Yeah. Okay, again we use func tools to decorate things. We import our get key, and we use it again a global dictionary as our cache. So most of the time it caches some kind of dictionary-like thing. When in Python, of course, you use a dictionary. So because you always need a key and a value to store. And then we write a decorator, and this decorator is different because it's a parameterized decorator, so we have yet another layer on the decorator. I don't know how familiar with decorators, but you can write parameterized decorators, and this one is usually done having this three nested level of function definitions. The outer one takes the parameters for the decorator, and the get key is in our get key function. So you could, if you want to define your own function that generates the key. So if you're not happy with it, you can do the other one. And also the cache. The cache is a global dictionary, but you could also provide a different dictionary. Any different dictionary you give it, it would take it. It just has to be a dictionary or behave like a dictionary for what we're doing. Okay, and then we have this next function which takes a function that's to be decorated, and then this is a function that replaces a function to be decorated. And again, we use the reps to get a nice doc string and a name. And then we just use our get key from the function arguments, so to produce a string which is unique. And then we just go in our cache. And if things are on the cache, then we just return the result. And if not, we go and call the function, generate the result again, and put our result in the cache, and then return it. And then we return this function and this function. So that's what we need to do. So let's try out how this works. So it is easiest do it interactively. So we just go into our caching, and we just import cache deterministic here. Cache would interfere with cache deterministic. Okay, now I have imported it, and now it's very easy to use it as a decorator. So the typical use of decorators, you use add cache deterministic, memorize deterministic, and then now you could provide your own get key function and your own cache dictionary, but in this case we just use the defaults. And then we define a function, and we just define a very difficult function, add a and b, and we return a plus b. So that would be a function. And also what I do, I say time sleep. So I have imported time already, time sleep, just to show you that it takes some time, because add a and b is very fast. You won't see any visual effect. So add a and b. And now I call my function 1 and 2, and I press enter. Yeah, sorry, I have to, of course, if I do say sleep, I have to provide how long it's going to sleep, not only sleep. So sleep 1 second. Yeah. So it's a little bit strange editing here, but it should work. Okay, and now I say add 1 and 2, and it takes 1 second till it's called. And if I call it again, so I press enter, I get immediate result, because now everything is in the cache. So you can look inside in this cache thing, see, because you have the cache dictionary, and you see now this is a cache dictionary, and you see how what it generated. This get key function generated module name, which is main in this case because we work interactively. Add is a function name, and then you have the keyword, the positional arguments are here, and then the keyword ones are empty, and then I get a 3. And if I call it again, it just goes in there, does the dictionary lookup. This one is not. So if I say this is A and this is B, which would be essentially the same as the one before, and press enter until it takes a second because it's a different signature. So it actually is the same, but I use a different signature. And if I look at the cache dictionary, you see now I have a second entry, which also has this A and B as a. So the positional ones are empty, and A and B is here. But if I call it again, of course, now it finds it and makes it faster. So. Yeah, because it doesn't know that positional ones are the same as that's not in there. I don't know if you could poke inside the function and figure this out. Maybe I haven't tried, but that's how it works. So we have this cache, and you see now things coming back. But this is deterministic, because now, as long as this program is running, this cache will give this value back. So if it's running long time, and of course, 1 plus 2 is always 3, so there's nothing changed. But you might have some other functions that depend on other external factors, and you might not keep this for a long time. For here, you could go in, because cache dictionary, just delete the key, and then would be recalculated. It would be one way. Just clean the cache manually somehow. That would work with just dictionary, just can clean it. Or you want to put something in that makes this cleaning automatic, and this would be a non-deterministic cache. This is our next example. So this is deterministic, so it always gives the same thing. And now we have a small variation on this, having a non-deterministic one. And this looks very similar with a small exception. They only have an age. So you can define an age, and I have an age of 0. So what does it mean? So everything is very similar, only now here I do a few other things, because I introduce the notion of being deprecated. So I can deprecate, so I can clean the cache, depending on some conditions, and the condition is a age. So now I store not only the value, but also the age, the value age. And if this age is not 0, and the value age plus the age, which is a time, is less than time. So my current time. This case time is okay, so we don't need so high a resolution. Gives me the current time step. If this condition is true, then the thing is too old. Then I say it's deprecated. Yeah, so it's older than this age, this 5 seconds, 10 seconds. Then I want to deprecate it. Or if I give age 0, then there's no caching. It will never be deprecated if it's 0. But if it has some value, it will be deprecated. And then, also if the key is not in there, we use the same mechanism. We also say it's deprecated. It's not there. So if it's deprecated, so if it's not deprecated, we just can return the value. Otherwise, we have to go on and calculate the function again, but also make a new timestamp. With time, we make a new timestamp and store both of them. There's a tuple here, time, and the function, and we store both of them, because up here you see we get both out of the storage, the timestamp in the value, and we put 2 in here, and then we just return storage key 1, which is a function argument here, a function result. Yeah, this is just very simple. So we can say now this function, this one has an age. So if we have 0, we use 0, we have the same effect as before, but we can specify an age, and then this thing will be deprecated, and the cache will be cleaned. It will be, will be calculated anew. So if we like to. So if we do the same thing, and we go to under interactive shell, and we import a non-deterministic cache. Non-deterministic. Okay, so if we do this, now we can actually use this the same as for our function. Just decorate our function and see what's happening. I say decorator cache non-deterministic memorize non-deterministic. My function add, which takes A and B again, and again I sleep. And this time I sleep a bit longer, so we can see a better effect. Sleep 5 seconds. Return A plus B. So now I say add 1 plus 2. I press enter. Yeah, I have forgotten to put the parentheses because it takes the age. So I have to put parentheses, and I say, let's say age is 10 seconds. Yeah, because I have to put the parameter in there, otherwise it gives me an error. Okay, now I say add 1 plus 2. Yeah, it has to be an age. Thank you. So it's have to, because otherwise it goes by position, and I give it a new cache. So it has to be age, has to be keyboard argument. Okay, yeah. For the other two can also be specified, and then it takes the first one. Okay, now eventually we got it. Yeah. So see. Yes, if you do it sometimes, you're so close you don't see the problem. Okay, now it takes 5 seconds. It takes 5 seconds, and you retrieve the tree. And if I call it again now, it reacts very quickly. You see, it always. But now, after 10 seconds, now 10 seconds over than the first call, it recalculates again and waits again, and takes a while. So that's what happens. The age is 10 seconds. After 10 seconds, it will recalculate everything. So that's a simple non-deterministic cache, and of course you can get more fancy. How you determine that's deprecated, you can do whatever you want. But also this you have to take it with some caution, because this caching is not for free. You see, I do quite a few things. I look in dictionary and calculate this and this. If it's just for A plus B without a sleep, it wouldn't make any sense, because A plus B is much faster than doing all the caching. So it's only worthwhile if your function is kind of expensive compared to the caching thing you have to do. Like if it takes 5 seconds, and then of course that's no question. But A plus B is just taking the function call is much more expensive than the A plus B in general anyway. So it doesn't make a lot of sense to do it. So it depends very much on your application if you cache or not. But if you identify something that takes very long, and you say, okay, I'm doing it all again and again and again, and would get the same result, I can add some of this caching. Okay, good. That would be caching. So let's shift gears a little bit here. After the caching, I would like to come to our example. So I have a small example that's computationally expensive, and we would like to work with this example. So this example it's one of the very typical ones for using something numerical to make things very slow. So we would like to calculate pi, so just the pi you need for the circle, And one very inefficient way to do it is using Monte Carlo. So suppose we have a circle. So there's a circle, and just one part of the circle here, one quadrant, and this is the radius is just one of our circle, and then we have a square which has all those, both sides are 1. And now we start throwing darts on this thing, and we know, we are guaranteed that all darts always hit within the square, but randomly a few of them also hit within the circle. You see, I use squares here for the one that hit into the circle, and small dots there, which one hit outside. So we know the number of throws we have, and what we want to know, we want to count this number, because if we do a little bit mathematics, we can calculate pi with it. So it's very easy, because we just take the area of the circle is PR squared, and then this is just PR squared, and this is just the quarter of the circle divided by 4. This would be this area, and this one, the square is just R squared. You have both of them, and now if you put them both in relation, this area to this area is just the same as this both formulas, and you rearrange a little bit, then you can rearrange and say pi equals 4 times the ratio of both areas. Very basic mathematics. So 4 times the ratio of both areas gives you pi, if you know the areas correctly. And now we, instead of using the ratios themselves as a proxy, we use the amount of throws of darts we throw on it. And if we throw an infinite number of darts, we get some good value for pi. We get pi actually. But since it's not possible to have an infinite number we have a big problem. So we just throw, and so our formula is written down. It's a little bit small here. It's just the number of points inside divided by the number of total points times 4 would give us pi. So that's what we do here. And I have a very simple implementation how to do it in Python. And then we do this different ways. Just open this in Python. No, I want to open. So I open this in Python. Plain pi. Looks like this. So that's our function. And in this case, I just import measuring, so I append something in my syspass to make it work here without doing anything. But this is a function that takes. We have the number of total throws, and now we just want to count how many are inside the circle, and that's pretty simple. So we go through all those throws, and the count inside first is 0, and we generate 2 random numbers. There are random numbers between 0 and 1, and if you look at this thing, it becomes obvious. So we have a random number between 0 and 1. This is the first one. The second one is just the coordinate of your point. And then what we do, we calculate the distance between 0 and our point. And if this distance is less than 1, then we're inside the circle. And if this distance is bigger than 1, then we're outside the circle. So the distance is just between here and the center. And this is the line where the distance is exactly 1. So everything that's 1 and less is supposed to be inside the circle, and everything bigger outside the circle. So we count only everything that's inside the circle. That's what we do here. Pretty easy. We just have random numbers, and we use Pythagoras here, the squares of x and y, and then the square root. Actually, because everything's between 0 and 1, you wouldn't even need a square root, but I put it in to have the complete algorithm. And then if the distance is less than 1, then we increment our count inside. That's a whole operation we do. Okay, and then I wrote a small helper which I import here, which is called measure time. This is a small helping function that makes it easier, more convenient to test a lot of different functions, because we're going to write a lot of variations on this one just to see which one is the fastest. And this one is contained in measuring. It's called measuring time. In the measuring subfolder here, measuring, and it's called measure time. And it looks like this. And this is just, this time it's not a decorator. I decided to use just a normal function that takes the total number of throws and then the names of the functions you want to call. And then its names. Yeah, so it's several names, and then I go through here, go through a list of all the names, and run this time it runner. So time it has a, you can use time it to do the timing in this case, and this one just takes a small string you evaluate, and this string is just the name of the function here, and we have to import this function. This is the setup, so we have to import the function from main where we are to make it visible and then run it. So it's just we generate a short string of Python code here, which is actually just importing the function, running the function, and doing the timing for us. In this case, a little bit different. See the variation, what you can do with timing. And then we just go through all the names of functions and run. So far we have only one function named the plain py, and run it. And then we just generate a table down here. I don't know why it doesn't scroll down. Somehow my mouse. Yeah, so it doesn't like me. So the mouse obviously doesn't take my mouse clicks. Just to reconnect it. Yeah, something is, because this one works, but this one is, yeah, I don't see it. This might be off the screen somewhere. Yeah, I hit it, escape. Oh, doesn't like me. Okay, yeah. It's frozen now. Just go to it doesn't go to the P. It doesn't go there. Yeah, that's it. So just open different editor. Okay. Okay, now somehow it's frozen, so I don't want to fiddle with it. Okay, now it's just, and this one is just formatting a table here to make things look nice. That's nothing very essential. It's just taking the results from the function run, and then it's just some tests done here to see how it looks like. So if you do this, now I just go into the directory and just run this one, and now we see calculation. So this is a 3.14, which is kind of close to pi, and now we have our table, and our table, of course, now we have only one function. It's just this one function, so now we will add more functions. This is just a meta function that runs our function, times it, and produces a table, and the only thing we have to specify is the name of the function, and it will run it. So if you do this with plain Python, so we get 0.4 seconds. Okay, and now we say that's too slow. We want to get faster, and now we try to do different strategies to make things faster. And the first thing I thought, I use square root of the squares of x and y, and actually the math module has one function called hypod, which is doing exactly the same thing. So if you import math, the built-in Python math module has a function that's called hypod, and this gives you help here in EuroPython. And you see, it's doing the same thing. It's doing the square root x squared y squared if you have this x and y. And I figured, okay, this must be faster than doing this by hand, because I just give it to Python, and Python's doing it once. And so I wrote a version that is actually doing this, and it's called math. So it's the same thing as essentially, But the only thing now, I use a hypod, and I just inline the random calls here, have these 2 random calls, and I just calculate the distance, and using hypod. And again, now I just do some import. I import plainpy and my measure time, and give it this name, and have this name, and call my function with. Now I just have to provide 2 names here, and we call both of my functions, run it 100,000 times with 5 repeats, and generate a table. So if you do this, so you run the mathpy, then you should see a result, and you can compare if things are faster. And you see here, this is actually faster. I use it with different Python versions, different operating systems. In some cases, it's slower. So actually, if you look at the material, this is not always faster, but it might be slower later on. So this is this code here. And you see, it's a pure Python version, and this is a math version. And then I run it, and see here, this is run a different operating system, and actually this hypod is slower, which I didn't expect at all, and has something to do with the implementation details, how this math module works, and how things are internally, and what kind of precision they use, and all kind of things. So, of course, I was pretty sure if I use a built-in function in Python, that's faster than doing it myself. But in this case, it was not. But obviously, on this machine here now, it is. So it depends very much on the, because now you delegate something to the underlying library, and then you depend how fast this library is. And it might be different on different operating systems. So Python's largely operating system independent, but in a few things this abstraction leaks. You know, this leaking abstraction thing, now it's just going away, and then you see things. And here I was very surprised that it is slower, whereas in the other example it's actually faster. So that's a big big surprise. But now when we do this here, I'm a bit faster. So I'm here, I'm about 30%, whatever you want to calculate, so factor 25% faster doing it with math than doing it the version before. Okay. Let's go to the next topic. There has been a talk about PyPy already, and the people, Armin Rigo, who also developed something called Psycho. Unfortunately, it's not maintained anymore. It's only for Python 2.6 and only 32-bit PC architecture. So any other platform is out. But I still want to show it because it's an interesting thing. It can be useful. So if you work on this type of platforms, then it can be useful because it's very easy, very easy to use, and you might get some speed up. So it's always worth to try. You might pay with some memory. So this has memory. It needs more memory. So you pay memory overhead for CPU speed. So if this is what you want, then Psycho might be useful. So you just have to import Psycho. When you say Psycho full, then Psycho is just in time compiling your whole program. It's just these 2 lines. That's it. You can also, if you like to, with Psycho, use log on profile. Then it's doing some log profiling in the background and just optimizes. You can also specify what you want. Optimizes the slowest functions. Just in time compiles only the slowest functions. Of course, Psycho only works for pure Python. Everything else in C extensions is not reachable for Psycho. And you can also bind things. So binding means you generate just explicitly for this function a just-in-time compiled function. If you do binding, then you just-in-time compile this function, only this one, nothing else. Then you can always be very explicit. And there's also one that's called a proxy, because if you bind it, you lose your original name. If you don't want to use the original name, you can use a proxy. So you keep the old function and the new function both. You just have to give the new function a new name. So you just say, this is my slow function, and you use proxy, and you get a fast function. You can call both of them at the same time. So that's how this works. And that's pretty much all you have to do. And then you can run your program and compare. So now I have Python 2.7, and it's a 64-bit, so it doesn't work on this machine. I have a virtual machine and it runs in. But it's still interesting to know that the things are possible. And the problem is porting to 64 bits is a very major undertaking, kind of rewriting the whole thing, because everything is somehow tied to 32 bits. So nobody has done this yet, but it seems like it worked. And for some examples, especially for this kind of example, because this example we have is just a loop over integers and doing calculations. And this type of thing is very nicely optimizable with Psycho, when you can get quite a few orders of magnitude out without doing a lot of effort. So Psycho is it's a low-hanging fruit. You can easily do it and try it, and that's all it needs. Just add a few lines and then see if things go faster. Okay, that's Psycho, but as I said, Psycho is not maintained anymore. The new kid in the block for quite a while is PyPy, and PyPy, of course, has a lot of the technology that Psycho has, or at least the knowledge is in there. And PyPy, to use PyPy is very easy also. See, now we have this program, and instead of Python, I just say PyPy, and that's all I need to do, and run it with PyPy. And of course now we cannot compare relatively, but absolute numbers. And you see, this runtime goes down from 0.32 seconds to 0.08. So that's a factor of 4 faster for this use case. So without doing anything, just using PyPy, it will be faster. And I think if you use a bigger number, you will see more effect, because now we use a small number, 100,000, and post PyPy uses a JIT, and you might heard about warming up times of the JIT. So I go up to 1 million here, and go with a repeat down to only 1, so it doesn't take that long, and run it again with PyPy. See, that's how long it takes with PyPy, and this is how long it takes with Python. And you see now we have a factor of 5 or something like this. Yeah, the mass one even. Yeah, we have to compare the right one. The plain one takes 0.13 seconds, and here the plain one takes 0.9 seconds. So it's a factor of, I don't know, 7 or 8 or something like this. So you can see quite a bit of difference. And if you go bigger, then you might see a bigger difference. So because then you give the JIT more time to warm up and see that things are slow, and where it's worthwhile to just-in-time compile. So if I do this now, that might take a while. I just run it with Python, and that's very easy. But of course, it's an example that is very well suited for optimization in PyPy. It takes a while to run, and then we do the same thing in PyPy. It should be quite a bit faster. See, now it's this one, 12 seconds for the mouse version. You see, if I do this one now, the mouse version is slower than the plain version for some reason. I don't know why. And I do the same thing in PyPy, and then it should be a bit faster, and we can see the effect. You see, it's 1.4 seconds for the plain one compared to 12 seconds. So it's quite a bit of difference. So it's about an order of magnitude faster for this type of things. So that's pretty impressive to see, because it's a use case that's optimized for doing these loops over this and doing some numerical calculations, because PyPy can figure out it's just doubles and integers there, and can just-in-time compile things accordingly, because it's pretty easy. Okay, so that's one option to use PyPy. Just right now it will be more like a test, I guess, because a lot of modules are not there yet you can use, but still it's interesting to see what you can gain with PyPy and how much faster you can get. And you can see both of the versions are pretty similar here, because it seems like they are pretty much the same, because the math module itself is also written in EuroPython, actually. So EuroPython is the implementation language of PyPy. It's a restricted Python, which doesn't have, for instance, doesn't have complex numbers, things like this, but it works with doubles and integers. So it's mainly Python with some restrictions. Some things don't work, and with types. Okay, so but there are other things in Python. So if you do numerical things, then NumPy might be something interesting. But also for other operations. So NumPy is an interesting library if you ever need some kind of homogeneous array. So if I import NumPy, very often you just call it as NP, so you don't have to type so much. Then you can work with arrays. So arrays are pretty different than from lists because they are multidimensional arrays. So if you need to work with arrays of, you see this can do a lot. So I can have an array something. This would be an array, the numbers 1, 2, 3. And now if I work with those arrays in NumPy, then usually you do element-wise addition. So if you do the same thing with a list, you wouldn't get concatenation. So it would have, the list would be twice as long with 6 elements repeating 1, 2, 3. With an array, pretty much everything is element-wise. So it can be interesting. So NumPy arrays are implemented in C, so they are fast for if you have large arrays and also multidimensional. This is a one-dimensional, but you can have as many dimensions as you want. So you could have my array B. There's something called an array range. A range 16, and I can reshape this thing. Reshape 4 by 4. And B now is a two-dimensional array. You see, if you do array range is very similar to range. You start at 0. You can also specify start and end and a step size, and here the step size can even be float. It doesn't need to be an integer. And then I can reshape it 4 by 4 and have a 4 by 4 array, and I can work with this 4 by 4 arrays. And of course, if I add two 4 by 4 arrays, I end up with another 4 by 4 array, and you see everything is element-wise. So 15 plus 15 is 30, and 11 plus 11 is 22. So that's pretty much how NumPy works. So it is very close to MATLAB, if anybody knows about MATLAB, or other similar systems where you work with arrays, and you can manipulate these arrays quite a bit, and you can do things. So you can slicing and all kind of things. So you can slice. If you slice this array, then you would get the first line. So you always go by line. Or if you want the first column, you would do something like this. You get the first column of your array. So this would be, so 0 is the first line, and this one would be the first column. So you can do a lot of things, and I do have a whole day course about NumPy, which is a pretty sophisticated tool, and also now is under heavy development, gets new features, and very nice. So let's use NumPy for our example and see what we can gain using this interesting library. So we use a very small part of this library, and we go to NumPy and we open it. And this one doesn't get bigger. So you have it on your. So if it's in the back, you cannot see it. Please open it in your editor. And now it's very different. So we don't write any loop. That's the main thing in NumPy. You want to avoid loops to make things faster. Because if you avoid loops in Python, you push the loops into C, and they are fast. So very fast. And that's what we do now. So we just have here. See, we have NumPy. Random has a random function, and rand is doing the same thing, and we give it a total number, and this returns an array of total numbers. So if I do NumPy random rand, I get NumPy random rand 10. I get 10 random numbers between 0 and 1, and I don't have to write a loop to generate them. And that's what I do here in this example. I generate two arrays with random numbers, and then I run this, and then I do the square root again. I do this x times x and y times y, but this one would multiply whole arrays with each other and give me the distance, which again is an array, and I just have to now figure out which part of this array is less than 1. And there's a very interesting thing. Again, you don't have to write a loop. There's a thing called where. So I say NumPy where, and it provides a condition. When I get a condition, and everywhere where this condition is true, I get a result array, and I just need to have the length of this one. But this one has two parts, so I have to take part 1, 0. So again, there are a lot of those built-in functions, and there's not a single loop in here, but it's doing loops in the background. The disadvantage is you pay with memory. You allocate all these arrays in memory. Most of the time, that's what you want with NumPy because you want to do a lot of fancy things with array. In this case, you wouldn't need it actually. So if you go bigger with a number, we'll see. If you go like 10 to the power of 8 or 9 something, you will run out of memory because you cannot allocate so much memory. Because not only one, you have X and Y are arrays and this are arrays. And they are still around here. Of course, I need them, so you have at least 3 arrays. And when you multiply, NumPy generate in the meantime might generate intermediate arrays. So you end up with a bunch of those arrays, and you pay with memory. And you need quite a bit of memory to do bigger problems. Most of the time, you want this. Because you can put more memory in a machine, but you cannot make the CPUs faster. It doesn't really work. So, but you can put a bunch of memory, so you pay with memory for CPU. That's what the thing is doing. And now we can try it out. So we can just go in our math P here, go to the 10, and we just say import. I would say from NumPy underscore pi import the name of the function. So it's just the pi NumPy it's called. So we just can import this name of the function, and then we save it, and we put this name of the function in our list of functions, and it will be run by our system. So, and then we just run our mathpy again, and you should see also with Python. This one doesn't work with PyPy because NumPy doesn't exist yet. And you see, now our NumPy is about 6 times faster than our Python. Pure Python version, even though we do a lot of memory allocation and stuff, we are quite a bit faster using NumPy. So if you have the right problem, then this NumPy might be an interesting tool for you. So it depends what you want to do. And there are also a lot of other tools based on NumPy. So if you want to do image manipulation, there's an extension to NumPy. It's called SciPy, which is much bigger, but it's very much connected with NumPy. And there's the one is called scikits for image processing. They have a lot of fancy image processing libraries based on NumPy, and they're pretty fast and very convenient to use from Python. Okay, this is NumPy, and PyPy also has a module NumPy. It was mentioned in the keynote, I think, and it's called NumPyPy, which is unfortunately doesn't run for our example because it doesn't have random numbers yet, so it hasn't everything implemented, so it doesn't generate random numbers. As far as I know, last week it didn't, so we cannot use it. But it would be interesting to see because this is written in pure RPython, or there's nothing written in C. Everything's written in PyPy or in RPython. So when it's supposed to be a replacement, or it has the same functionality as NumPy, it might be interesting to do. Okay, good. So now we did quite a few of things, but one thing we didn't do yet, we always worked on one processor. My machine has 4, some people might have 8 cores, and you want to use those cores. And you know Python has what's called the global interpreter lock. So even if you use threads, you run on one core, but there's one module called multiprocessing. And multiprocessing allows you to use several cores on one machine in Python. There are also solutions for distributed calculation, but multiprocessing has advantages. It's in the standard library, and you can use it immediately and can distribute your calculations on several processes. So let's have a look. Is this one still? Yeah, it's still. I have to kill this thing to make it. Okay. Let's look at multiprocessing. And I have a not the right one. I try to open this again. That is nicer. I can make things bigger. Takes a second. Let's look at multiprocessing, how multiprocessing does things, and actually there are several ways actually doing it. Okay, so we can go to multiprocessing. EuroPython code multiprocessing. Yeah, I missed multiprocessing. Close. Okay, and the first one is processes Py. So multiprocessing is part of the standard library since Python 2.6. So most of the people should have it. If you have to work with the older version, there's still a solution because there's a module called processing. So if you don't have a current Python version to work with for some reason, you can install processing. And that's what I do here. I try to import multiprocessing. And if it works, it's fine. Otherwise, I try to fall back to processing. And if it's still not there, then you have to install it. And it goes back to several older Python versions. So I need two things for multiprocessing. I need the process and the queue. So if you work with threads, then you can access global memory, global data structures. With multiprocessing, you cannot. You have to use a queue. So even if you use threads, it's always a good idea to use a queue because it's a very defined way to exchange data, kind of message passing. And that's what we do here now. We need a queue to exchange data. And the problem is if you work on multiple cores, you need to redefine your problem. You have to redefine your problem that actually can use multiple cores, which is not that easy. For our case, it's pretty simple because you see every of those throws is independent from the other. So conceptually, if you have a lot of actions that are independent from others, then they are supposed to be pretty easy to be parallelized. And that's what we do now. So we break down our algorithm in two steps. So the first one is just doing the counting inside, not the multiplication by 4 for the ratios. And this is pretty much the same algorithm we had before. We just do the count inside here, which is exactly the same as we had before. And then we have to do a few things to run it in parallel. And that's what I'm doing here. So you have another function that actually is just doing this times 4 of those ratios. And this one just calls the count inside. And then we have a function called count inside process, which takes the total. And now I use a queue. So I have a queue and have to put something in the queue. So the queue is a concept you can put something in and take something out. And this is a means of communicating between cores in multiprocessing. So I use a queue here to communicate with other cores and send some data. In this case, it's very nice because I only have to send this total inside. I don't have to send a big data structure, just one number, and the function. So the function also. Multiprocessing in the background use pickle to pickle things, and also has to pickle with my function to send it over, and create another process. And then I need to do a step which is called domain decomposition very often. So I have to cut down my problem into sub-problems. And this is pretty easy. I just say, okay, I have the total number of throws, and I divide by my process count. And I use floor division here, so it will be compatible with Python 3. So always I get the integer result. And so, okay, the minimum number of throws for each processor will be n. And then there are a few missing, and the few missing ones, so that to get the right number, I just multiply this one and make a list out of it with as many entries. And then I have a reminder which is left over. I do the Mollerv operator and get a reminder. So there might be a few leftovers, but this number is smaller than the number of processors. Yeah, if it is evenly distributed, it will be 0. It won't be any reminder. Otherwise, this number will be smaller number of processors, and you just take this number and just distribute it over the other one. So that means every processor has pretty much the same number, at most one different. So for big numbers, it doesn't really matter. but at least we are consistent, we have the right number of throws. And then I have a list for my queues. So I make an empty list here where I would like to put my queues inside. And so I go to my counter and generate a new queue. So for every counters, if I have 4 processors, I would like to run 4 processors. I need 4 queues to connect to those 4 processors. That's a way to connect with them. And also need to have 4 processes here. And this is very similar. Whoever works with threads will recognize a lot of similarities. So the API is very similar. So we generate, instead of a thread, you make a new process. And here you just give it as a target. I provide my count inside process, this function up here. Count inside process will be the target. This will be run on the other process. So I have to tell them, okay, this function, and then my person has to move this function to the other process and run it for me, and gives me the result back. So you have to have this one, and this one is just the counter method here. And you see, and this counter message is calling this function and puts the result back in the queue. Because this function has to communicate back to the mother process to give the result back. And that's what I'm doing here. And now we have the process, and then we use process started. Very similarly to using threads, I have to start the process, and then I append this one. So this is asynchronous. I start everything and append it, and then those things go off, and then I can wait for the result coming back in the queue. And to do something, I have to remember those objects I created, and for this I use a queue and a process as a tuple in this case. And then the only thing I have to do now, I have to go to the process. Process 0 is a queue here, which I have here. And I say get, and get the result for all processes in my queue processes thing. So I have this loop over it, and now I get the queue. Process 0 is a queue, and this I ask this to get, and this get gives me back what this puts in there. So put is one side, so one processor puts it in, and the mother process gets a number out. So the first thing is I have this one, I create a process, send the process a function, and the argument to run the function. This function calls puts the result back to the queue, and the mother process, which I have here, is taking it out and sums all of them up. Yeah, and then I go through and wait till all of them are finished here. Actually, this get is blocking already, and I just wait till this processes are finished, and then I just calculate my inside count divided by the float of total. That actually gives me my pi. So, and now I can specify how many processes I want. In this case, I want to have 2 processes. Yeah, and then the total count is 1000. And in this case, I just break out a little bit of this when I just do this timing by hand, just to compare without no processes, no multiprocessing, and 2 processes with multiprocessing, and see the ratio between the times and the difference between the times. Here. See how this works. We run this. So we go to multiprocessing, and we call our process pi. Oh, I must have changed something. Obviously I changed something and didn't try. Okay, so there's no time, because there's it's called one time there. So please rename this one to one time. So I renamed it and haven't been consistent. So it's one process, the other one's 2 processes, not no process. So please rename no time to one time, and this hopefully is doing it. Yeah, so now I have a result. You see, a bit bigger. I have a result, and see the runtime for one process is much shorter than the runtime for 2 processes, because now I have the overhead starting in the external process, even though it's just a fork. If you do this in Windows, the overhead is even much bigger, because then you have to do a lot more things to start a new process, and I'm only 100th of the time as fast. So this is going to change if I make this number bigger. So instead of only 1,000 here, I just say I go to 1 million and see what it's doing then, and run the whole thing again. So I run the 1 million times, and now you see if I do it with one process, it takes 0.8 seconds, and with two processes it takes only half a second. So I'm faster already. So you can see the maximum the theoretical maximum, you would be twice as fast. Of course, you really are unlikely to reach it because there's always some overhead. And then let's crank up the number a little bit more, 10 million times, and then you should be faster. So it should be now around like 10 seconds or so. And then you should get close to the maximum number you get. So with one process 8 seconds and the other one 5 seconds. So very similar ratio. So that didn't change a lot. You see, the ratio is pretty much the same. So it doesn't matter if it's power 6 or power of 7. And you can also try to increase the number of processes you run with it. So stay with 6 here, but go to 3 processes. And see what happens if you see some differences. So now theoretically it would be 3 times as fast, now and twice as fast. So with 3 processes, about twice as fast, and it's pretty much as fast you can get, because you always have some overhead. It's impossible to always increase the things. And if I do 4 processes, actually I think it's getting slower. So I have 4 cores, but it's some kind of virtual kind of things inside. You never know really what are real cores and what are virtual cores. I think it doesn't get any faster if I use 3 cores or 4 cores. A little bit, so, but you run again. It's pretty much the same time. So you might run the other one again with 3 to get the same result. So most of the time, it's my experience, if you run it with 1 core less than you have, then you're as fast as using all the cores. Because all the 1 core doing something, operating system stuff, and we have more switching. So with 3 cores, you can get twice as fast with this multiprocessing. So this kind of works, and you can do things. But it's still kind of complicated if you look at it. You have to make a queue, and you have to send things, and all this workers do exactly the same thing. And for this case, there's a second way to work with with multiprocessing, which is called the pool of workers. You can use a pool of workers, and you can work with it. So let's look at the other one. This is called the pool, which just makes things a bit easier. Of course, then you have this master-slave kind of thing. So, and here you import pool and also import CPU count. So this multiprocessing module has a CPU count, so you can actually count the CPU. And this gives me a number of 4. If I import this, I get a 4 for my machine. You might get a different number. So it also usually it asks the operating system. Operating says 4. So that doesn't mean you have really 4 cores. Some all those hyper-sorting things might count also. Yeah, and then I make things easier. The count inside stays the same, but now my parallel part is getting a bit easier. So I can now just define the number of workers I would like to have. And I don't specify any. So if the workers is none, then I just take the CPU count. So I can ask CPU count, give me the workers. And this is a domain decomposition, the same thing as before. But now things get easier. Now I just can make a pool, and the pool just has a number of workers I would like to use. So there's no explicit queue and no explicit process I generate. I just have these workers, and then I just say pool. You see here what I get here. This is for workers. Pool apply asynchronous, and they provide the function object and tuple with the arguments. It's only one argument, so a tuple with one element is just with a comma here. You need a comma. That's my arguments, and for all counter encounters. So I apply this function asynchronous on all. So I have this. The master is asking all the 4 slaves, or how many workers I have, to do the same function. asynchronous. So I just call the function, but it does not block, does not wait for the result. That's very important. Otherwise, if you call one after the other, then you don't gain anything because you block. And this is asynchronous and makes things much easier. You don't have to bother about queues and processes. You just can go and call this asynchronous. If you have this use case as we have here, every the workers doing the same thing. If every worker is doing something different, then you might need to go with queues. But that's very nice. And then it's only one line. We say result get, and this result get actually is just retrieving the result from here, from this list. That's a list of those kind of, if you're familiar with other kind of synchronous frameworks, sometimes it's called the future or whatever, it's something you can call later to get the result. But it's not the result of the function itself, but something that gives you access with this is get to the result of this function call. And this is how this asynchronous things work. So you have this object result here, and then when you in this moment you call get, it's going to block. But it's fine because all these workers are supposed to be finished, and now you get the results. There's no error handling. If some of the workers is crashing, then you might wait forever if this is blocking. But for this simple case, we just use get, and now we get a result. We sum it up, we have the count inside, and then we do the division by 4. Those much nicer, much shorter, not so much effort, easier to use. And then if you run the same thing, let's go up to power of 6. Then you should see a similar result. So it's not faster because in the background it's doing the same thing actually. So if you run this one, okay, you see this, the times is about the same. That's a bit slower now. It looks like slower, but it's not necessarily the case. If you run it several times, you might get a bit different readings. You see the numbers vary a little bit, especially if you have most of the laptops. They have a lot of power saving functions in, and if you don't turn it off, then it might take them a while to wake up and get some good results. Okay, that's what you can do with multiprocessing. So it's very similar to working with threads, but you can use multi-cores. Of course, you need to have a task that is worthwhile to decompose in subtasks that can run long enough in separate processes, and then you have to send it abroad and get the calculator and get the results back. Depends very much on your problem. Some things are easy to spread over several CPUs. Some are way more difficult. And it might also be counterproductive, might get slower. So if you have a lot of exchange between those things, you might lose way more time for sending data back and forth than you gain by getting faster CPUs. Okay, we can also combine things. So we cannot only have multiprocessing, we can also have combine this one with NumPy. So that's pretty simple. So now we have our count inside simplified. So we use NumPy, and so it's the same knowledge we had before. So we use NumPy here and have our count inside and do the same thing. That's what we saw before, and then the rest stays the same. We just use our workhorse, everything, only this one function. I just copied everything, have it in one file, but this is everything the same here. Nothing has changed. So, but we can use NumPy in all the workers. And if we try this, and I go to 1,000,000 and I run it with NumPy, and we can compare the runtimes. Pool NumPy. Then you see these two workers in this case is slower because we need import time for NumPy, so it doesn't make sense here to use it. Wow, that's a very different result. Yeah, so the two worker thing is faster than a no workers thing. I don't know why the times are so much. The times are faster. Yeah. So the first time had some overhead here to get started, obviously. So we have this effect. So you need to run it several times. And now if I go to 3 workers or 4 workers, you see a bit more improvement. So the improvement here is relative is not as fast as just plain Python, because the whole thing is faster. So the whole thing is faster than your improvement. And this is slower actually here again. I don't know why 3 workers are slower than 2 workers. And now it's faster. So you see this is now it's 1.3 faster. It depends on my machine. So it seems like it's gonna take some while to warm up to get the full speed here. So if you go a bit bigger, then you might even run out of memory quickly, because now a 10 to the power of 7 should work. But if I think power of 8, I get a memory error, and it tells me it doesn't have enough memory to do those things. Okay, if it's bigger, then you should see a bigger difference. So it always depends on your problem size. If the problem is so small, just this is way too coarse-grained parallelism that you can get anything out of it. So you have to have something that really fits. And the only thing to know is just the measure. So it takes 10 seconds without workers and 9 seconds with 3 workers. So you don't gain a lot, obviously, in this case. I don't know why it's a bad performance. Wow. Yeah, I don't know where this comes from, but there's something strange. So. Excuse me? Yeah. No, it shouldn't. It shouldn't, because the thing is you use random numbers anyway. So the value of pi is changing randomly because you use random numbers. And if you have for some reason have very good numbers, so the precision of it's not dependent on the workers, because you just spread it and they do the same thing. They do random numbers, and the random numbers they use the seed with a timestamp. They should be okay. Shouldn't be an influence. You cannot control anyway because random numbers. So if we will need to use this fixed C to compare things, but it shouldn't be a difference. But I don't see, this is kind of very weird kind of happening here. So you obviously have to run it several times to see what's going on. So it's very different numbers. I know. Seems like it has to do something with memory allocation, because this NumPy is pretty heavy on allocating these big arrays. And if it's pre-allocated, can you reuse memory or something? Some kind of effect. So the first time I run it, it takes not so long. So kind of consistent results. Why it takes so long? Yeah, so there's something going on here, which is not so nice. Yeah, so it's much slower doing several workers. So it's not necessarily faster, obviously. Even supposed to be, because the problem is when we saw this with pure Python, it's always been. But now we also have to import this NumPy over the place, and NumPy import takes quite a bit of time. So it's different if you don't run it once. You keep the workers running over a longer process, then you don't have all the overhead. For this one, we have the overhead once in the beginning, and if your things runs for hours, which is not uncommon for NumPy calculations, then it doesn't matter if it takes a second or 5. It runs for another 10 hours, so that's fine, and then you shouldn't see the big differences. Okay, so this would be multiprocessing. Multiprocessing things, so you can combine different kind of things. Good. Do I have another one? Yeah. So now eventually you could just, now what I'm doing now, I'm importing a lot of those different modules and run all of them together and just put them in here. You see I have a list of functions. It's just now, so because I have different versions. Sometimes you have NumPy installed, not NumPy installed. You have Psycho or not Psycho. And this is just assembling all these tests and runs all the tests. And if you run this, then you should get a bit of overview how things work. So this would be 100,000 times and one repeat. And yeah, so that's what you get now. You see, if you do 100,000 times, you get these numbers, and you do 1,000,000 times. So that's the plain Python version with workers. In this case, workers are faster than, I don't know why, than the single version one. And then that's the parallel run with plain Python. And this is a math one, and this is a plain Python one. See, it's a factor of 14 difference you get here. And if you go bigger, you should be able to go to a factor of power of 10 million. So Psycho is not found. If you have 2.6 and you have Psycho installed, it would also get a Psycho version, which is considerably faster than other things. Good. Still think about it. Yeah. See, the worker version is only slightly faster now than the not worker version, for what reason ever. And then now it's only 2 times faster for those big amounts. Because it seems like, of course, the arrays are big, so the memory allocation problem seems to kick in here, makes things slower comparable to the smaller one. Yeah. So there's always something changing. Good. So that's just a short introduction how to use multiprocessing. Of course, you can do it for other things also. That's just because we want to stay consistent with this example. And doesn't work. So let's wrap up things. So I put together like some overview what you can do to make things faster. The first, of course, you have to really make sure you need things to be faster, and you have to make a small analysis, and you have to measure. That's a big thing. And then you can see algorithmic improvements. You can get orders and orders of magnitude speed up. We had 3, 4, 5 orders of magnitude speed up depending on the data size. That's the first thing you can do. And with Python, you are very fortunate because it's very easy to try things out when you have very strong data structures. So data structure and algorithms are connected. So sets and dictionaries and the collections module, they offer a lot, and you can try out things very quickly and see how things work. So that's much nicer doing this in a lower-level language, which it takes you a lot of time to do this. Then other things are, we just used NumPy. So if you need to do numerical things, NumPy might be the answer to a few things. If you need to calculate things, Psycho can be interesting if you work in an older version of Python. PyPy. If you don't depend too much on C extension modules, then you could even use PyPy. Another one is Cython. We haven't covered in the course. So Cython is a mixture between Python and C. So you can easily link Python and C. You can just start with pure Python and add some type declarations, and slowly make your things faster. And you end up with a pure Python version, pure C version, pretty much written in Python. That's possible for some things, and that's very nice way to connect. You can also import C functions. So I have another course called Extension. We do Python quite a bit, which is interesting. The other one is C types. So C types is a part of Python standard library, and this one allows you to call DLL. So if you have this calculation of pi written in C somewhere in a DLL, you can call it from Python pretty easily without even recompiling the C. So somebody can give you the shared library, and you can call it. You can write C extension by hand, which is a very tedious thing to do. I wouldn't recommend unless you necessarily need it. You can use Swig and other things to wrap other kind of things. You can even wrap Fortran, and you can even go, if you like, you can go into GPU. So I haven't tried myself, but those things you can do, work on GPUs and things like this. There are quite a few tools out there in Python to do those things. Okay. So, see, I'm rushing through here a little bit because we had to finish everything in 3 hours. And I'm through. I would say thank you very much for your attention, and I will be available for questions.
So, if you want to make a question or two, we have 5 minutes or something. You want?
Yeah, so I will also be at the conference. So if you like, I have a booth. If you want, you can come and ask me questions. If I have anything you want to ask, just in person, and not in front of the crowd, we can look at things and try out things.
Okay, thank you very much.
Thank you.
Program. We are talking about JavaScript after the lunch here. And starts at 2:30. Ok, thank you. Io la lascio. Te vedi? Sì, anche.